Hello and welcome back. So today we will solve another past paper question from the topic waves, and this question is taken from 2023 past paper. And if you haven't solved the basic questions that we solved in the previous videos, like all of these, I would recommend you go back and watch the basic questions first, because this question is a bit more advanced, and in the syllabus we are here right now. So we will solve a question based on these two concepts. We will use this equation. This equation is an equation for speed of a wave on a string, and the speed v depends on tension in the string and the mass per unit length mu, right? This mu is mass per unit length. We will be targeting these concepts in this question. So the question is very simple. Basically, we have a wave and it is vibrating with some frequency f. The question is, the first one, describe what was observed as f was gradually increased to 2f. So if we change the frequency from f to 2f, you have to explain what will you observe on this string. Now, I have drawn some drawings on the right side. You can see what you have to remember is that if you have a string which is fixed at both ends, right? So there will always be a node at the point which is fixed. So this point is fixed. You can see we have a node here, and this point is fixed. We must have a node here. Once you understand this point, that I have to make, or I have to draw a node at the fixed end of the string, then you can easily make first basic frequency, second frequency, and third frequency for a standing wave. So this is the first frequency. If you have two nodes at the ends, you can make one antinode in the center, and this is what the wave will look like if it is vibrating at the fundamental frequency f, which is also shown in this diagram here. Now, if you double the frequency, you will see two antinodes formed here, and if you triple the frequency, you will see three antinodes in the string. Now, what we need to find an equation for frequency, or that relates frequency and wavelength, right? So the way you do it is, let's say the length of the string is L. So in this length L, if I ask you what is the wavelength of this vibrating string, if you cannot figure it out, what you can do is you can just complete the wave. So we have one crest here. We can draw a trough. So one crest and one trough. This is a complete wave now. And now you can easily see, if this is a complete wave, then this part right here, this must be only half of a wave, right? So this is half lambda. The wavelength of this vibrating piece of string is lambda over 2. So what this equation is saying is that in length L of the string, you have half of the wavelength, right? And now we can rearrange this equation for wavelength lambda. I can write lambda equals 2L, right? So multiply both sides by 2, and I will get lambda equals 2L. So now that we know what the wavelength is in terms of length of the string, we can write an equation for frequency. So we will use the relation between velocity, wavelength, and frequency to find frequency. The relation is v equals f lambda. And if you rearrange this equation for frequency, you will get that frequency equals v divided by lambda. And we already know that lambda is 2L, right? So I can write f equals v divided by 2L. And this is what I will call f1, because this is the basic fundamental frequency. Now, I want you to stop the video and derive the same relation for this diagram. This will be called f2. So let me just erase f3, and I can solve for f2. So we will do the same. We will compare the length L with the wavelength lambda. So in this length of the string, for this diagram, for the second diagram, you can see we have a complete wavelength in this fixed length. So in this case, L is just equal to lambda. And again, we will use our equation for frequency, f equals v divided by lambda, and lambda is just L. So I can write f equals v divided by L. And this is f2. Now, if you do the same for f3, you can see the pattern. And the pattern is that how if I want to go from f1 to f2, right? So what do I need to do to go from f1 to f2? I just need to multiply by 2. So you see, if I multiply f1 by 2, the 2's will cancel and I will get f2. What this relation means is that the second frequency is just 2 times the fundamental frequency. And that's the reason this second frequency is sometimes called second harmonic. Second harmonic. So the number of harmonic actually means this frequency, what multiple is it of the fundamental frequency. So if some frequency is second harmonic, that means that it is 2 multiplied by the fundamental frequency. If some frequency is third harmonic, that tells you that f3 must be 3 times f1. So this will be the third harmonic. But you should be careful. This type of pattern you only get for a string which is fixed at both ends. So for example, in organ pipes, if you have an organ pipe which is closed at one end and open at the other, right? So the first standing wave that you can get is this. And as you can see, this part of the wave, this is not half wavelength. This is actually a quarter of wavelength, right? So just 1/4 of the wavelength. And when you follow the same procedure and derive frequencies for organ pipes, you will see that you don't get second and fourth harmonic. You just get first harmonic, which is f1, and the next harmonic that you get will be the third harmonic, and next will be fifth harmonic. So there are only odd harmonics possible if you have a string or a cavity which is closed at one end and open at the other. Anyway, this question is about string which is fixed at both ends. So you will get second harmonic, third harmonic, fourth harmonic, fifth harmonic. And the important thing that will allow you to answer this question and any other question which involves the same concepts is that between f1 and f2 there is no other frequency. So for example, you cannot get f1.5 which is 1.5 times f1. This is not possible. Okay, so after the first frequency, the next possible frequency is second harmonic, which will be a whole number multiple of the first frequency. So this question described what was observed as f was gradually increased to 2f. The answer is that between f and 2f, there is no in between frequency. There is nothing. What you will see is that this amplitude will get smaller and smaller like this if you keep on increasing the frequency, but the shape of the frequency or the shape of the string or shape of the standing wave will not change. Okay, the amplitude will keep getting smaller and smaller, and suddenly you will see this frequency, this standing wave, right? Something like this, or I should point it here. So between this shape and this shape, there is no intermediate steps. So that's another way of saying that frequency on a fixed length of string is quantized, right? So in more advanced topics, you will see that we will call it the quantization of frequency for a fixed string of length. If the length is fixed, you can only get certain frequencies, and the frequency will always jump from one value to the next without going through intermediate values. So that's what I mean when I say that in going from f1 to f2, there is no point in between where you will get 1.5 f1. Okay, this is not possible. So it's really quantized. It's just f1 and the next frequency is f2. I hope this point is clear. If you have any questions, you can ask in the comments. The next question: a guitar has metal strings under tension. When a string is plucked, it vibrates, producing a sound wave in the air. Describe how the vibrating string produces pressure variation in the air. Now, this is just a descriptive question, and I have solved this question. How can you imagine sound waves in air? How the pressure variation creates region of high pressure and regions of low pressure? You should watch my previous videos. I'll just move on to the next question. And this question is very important. You can see, first of all, it has 4 points, and it will give you some practice to apply these concepts. So remember, I derived these frequencies for fixed length, which is fixed at both ends. And I really want you to learn the concepts, okay? Not just how to solve this specific question. I want you to learn the concepts that we are applying to solve this question, so that if you see another question, but from the same concepts, you will be able to solve that question also. So in this question, the guitar player plucks a string to play a note. A standing wave with one antinode is set up on the string. Now this is a key word, one antinode, okay? This has specific meaning. They want you to think in a specific direction. I'll explain it in a moment. The question is, he can vary the length of string that vibrates from 21 centimeter to 63 centimeters, which means that he can press at different positions, and that's how he can change the length. So he can press at here at this position, and the fixed length will be this. So he can change the length, and we have to deduce whether a note of frequency 196 Hertz can be played on the string. And we are given these things: tension in the string and mass per unit length for the string. Now these things, they are also like, this is key information. It gives you a hint that you need a specific equation. Now I showed you at the beginning of this video that velocity of a wave on a string is equal to square root of tension over mass per unit length. So because they have given you the tension and mass per unit length, you need to use this equation. Another very basic equation that we know is V equals F lambda. And we need this equation because, after all, we need an equation that contains frequency, right? So we have to deduce whether a note of this frequency can be played. And we also know that we need something that can be related to the length of the string. And I already explained that length of the string can be related to the wavelength, right? So wavelength can be related or can be derived from length, and also the length can be derived from the wavelength. So you see this length here, wavelength here, it has inside it information about length, these numbers. And now we have two equations for velocity. We don't know anything about velocity, but we are given this value. So what we can do is we can set them equal to each other. So we will get F lambda must be equal to square root of T over mu, right? Okay, so we figured out from this information that we have to use this equation. From the fact that we were given frequency, we knew that we also need this equation. And then they are both equal to V, so we set them equal to each other. Now the next thing we need is this wavelength, right? Some way we can get some information about this wavelength. And now comes the important point, this keyword, a standing wave with one antinode is set up on the string, right? What does that tell you about wavelength lambda? Now, if you have understood what I explained in the last part, you must understand that the wave that they are talking about having one antinode is this standing wave, right? This standing wave has one antinode. And I derived a relation between length and wavelength for this standing wave. It was, you can see here, it's lambda equals 2L, right? So lambda must be equal to 2L. By the way, you should understand that when we change this length from 21 to all the way to 63, we can use any length by pressing at different positions. The shape of the standing wave will not change, okay? We are still producing the same first frequency, but because we are creating it with different length of the string, the frequency will be different, okay? So the shape of the wave will be the same. So that's why this same equation will apply to any frequency, because we are still working with the same fundamental frequency, a standing wave with one antinode, okay? So that's why I can replace this lambda with 2L. So F times 2L must be equal to this. And now just rearrange for L. L will be T over mu, which is a mass per unit length, divided by 2 times F. Now the frequency that we want to play is 196. So you just plug in all these values. Tension is given 56 newtons, mass per unit length is also given, and you divide it by 2 times the frequency that you want to play, which is 196 hertz, and you will see that the length that is required to play this frequency will be 0.27 meters. It means that since we can change the length from 21 centimeters to 63 centimeters, if you convert it into centimeters, it will be 27 centimeters. It means that we can play a note of this frequency with the given range of length, right? So we can, since we can choose any length between 21 centimeters to 63, and 27 centimeters is in between this range, that means that this frequency, a note of this frequency, can be played on this string. So once again, the important point in this question was the fact that when you change the length of the string, we are not changing the fundamental frequency, okay? So it will be still the first standing wave, the basic standing wave, just played at a different length of the string. And because it's played at a different length, it will have different frequencies. And we use this information to use this wavelength lambda here in this equation. If, however, if the shape of the standing wave changed, for example, from F1 to F2 like this one, then you would need to use a different relation for lambda and length. In this case, for this diagram, length is just equal to lambda, right? So be very careful if you're solving any other question from this topic. You have to choose the length or the relation between wavelength and length accordingly. In this question, this relation was based on this diagram. If you have some other diagram like this, you need to use the relation between wavelength and length accordingly. In this case, it will be lambda equals L.